Okay, I think everything seems to work fine. So welcome everyone to this very first seminar, which is first time in a hybrid way. So we have people here in the Copernicus lecture room, and you're on the camera there. You can have a look where you are. You can wave so that speakers can see you. And we have our speaker today and people from different places joining us via Zoom, as it used to be in the last year. So I'm very excited that we try this. We meet humans eventually, after a while. A couple of remarks. We're obliged to wear masks. I'm taking my mask off when I'm speaking, but then I'll put it on. So the masks, the distance, there are some ticks on the chairs here. So keep your distance. And then the questions from the audience, please ask them to this little microphone so that then you can be heard by the speaker and the people in the audience. So I think everything is set up, everything works. Michal can see us, we can hear him and see him. So I'm excited to announce the beginning of Tuesday seminar series with Michal Drahus from Cracow Astronomical Observatory, who's going to tell us about Oumuamua. Sorry, I'm never able to pronounce this. Michal, please.
Hi, everyone, and thank you for joining. Also, many thanks to Łukasz for inviting me here. In fact, Łukasz invited me several times already, so I'm very happy that it finally worked out. The purpose of this talk is to give you an overview of the first known exosolar minor bodies that arrived in the solar system from interstellar space. To date, only two such objects have been discovered. One is known as one-eye Oumuamua, and the other is called two-eye Borisov, where I stands for interstellar. The talk will be split in two parts, each focused on one of these two objects, or maybe even in three parts if a third one is discovered sometime soon. So today I'll be talking about one-eye Oumuamua. When it comes to two-eye Borisov, our team is still working with the data, including an excellent data set from OGLE. It's been a great pleasure to work on this with Professor Andrzej Udalski and the rest of the OGLE team. And I'd like to take this opportunity to thank everyone involved in these observations for your efforts. This data set is so good that you want to extract every piece of information from it. So this, of course, takes time. But after we have completed our analysis, our team will be back in Warsaw, hopefully in person, with part 2 of this talk, then dedicated to two-eye Borisov. But today I'll be talking about Oumuamua, this funny object with even more funny name. Of course, we all realize that Oumuamua, despite this funny name, is a scientific treasure. And that is because unlike millions of comets and asteroids that formed in the solar system, Oumuamua is not from here. This body formed around a different star and then entered the solar system from interstellar space. And this is why it is so unique. So the obvious first question to ask about Oumuamua is why it actually left its home system and set off for this long, very long, maybe millions of billions years long interstellar voyage. So the honest answer is that nobody knows for sure. But we may learn something from the early history of our own solar system. So here you're looking at the dynamics of the early solar system. I'll play this movie again in a second. Anyway, let me make sure that you see my cursor correctly. Okay, good. So I play this movie again in a second. So here you're looking at the very early solar system. This innermost orbit is the orbit of Jupiter. Then we have the orbit of Saturn and the two ice giants. And now you don't see the orbit of Mars, Earth, Venus, and Mercury, because this epoch of the solar system is so early that the terrestrial planets don't even exist. Blue dots are icy planetesimals, while the red dots are rocky planetesimals. And see what's happening here. The orbit of Jupiter will start shrinking. So our Jupiter really wanted to become a hot Jupiter. But at some point, something amazing happens. So please see it again. The orbit of Jupiter shrinks, and then look, the orbit of Saturn starts shrinking as well, and then both planets move backwards towards wider orbits. So it really looks like Jupiter desperately wants to become a hot Jupiter, and then at some point Saturn joins and removes the Jupiter from this very hot environment. As a byproduct of this situation, four terrestrial planets formed. This is exactly because Jupiter wanted to become a hot Jupiter long time ago. But there is also one interesting consequence of this situation. As you can see, at the end of the simulation, there is far less dots than before. And that's because this simulation shows a period of dynamical instability, which basically exploded the inner solar system. And as a result of this, over 90% of primordial asteroids and comets were ejected into interstellar space. So the moment when Saturn and Jupiter start moving away from the sun is when they enter a mean motion resonance 2-to-1. So two orbits of Jupiter versus one orbit of Saturn. This resonance was so strong that it pushed both planets backwards and allowed the formation of the terrestrial planets. So dynamical instabilities resulting from mean motion resonances are really capable of exploding, dynamically exploding planetary systems and eject a plethora of minor bodies into interstellar space. A similar episode happened in the solar system much later, when the solar system was almost 1 billion years old. So it's really much later. Sorry, I wanted to say much later. So here you can see the architecture of the outer solar system this time. The bright blue circle shows the orbit of Uranus, not Neptune. This is the Uranus. Then you can see the orbit of Neptune, and then two giant planets, Saturn and Jupiter. About almost 1 billion years after the formation of the solar system, the two giant planets, Jupiter and Saturn, again enter a mean motion resonance 2-to-1, and this again causes a tremendous chaos in the solar system. As a result of this, Neptune comes closer to the sun than Uranus. Sorry, the other way around. Uranus comes closer to the sun than Neptune, which is not how it all started. And also, as a result of this, the outer solar system this time dynamically explodes. And as a result of this, nowadays, we see in the Kuiper belt only a small fraction of the primordial objects that initially formed there. The rest were again ejected into interstellar space. So two episodes of mean motion resonance 2-to-1 between Jupiter and Saturn, and we had two episodes of catastrophic instability in the solar system. So by analogy, we expect that the same can happen in other planetary systems. And as a result of this process, planetary system may populate interstellar space with great numbers of comets and asteroids. And perhaps Oumuamua is just one of them. Now, let me quickly introduce you to the discovery and early observations of this object. So Oumuamua was discovered by Pan-STARRs, and it was in fact very faint at the time of the discovery, and without Pan-STARRs, its discovery wouldn't probably be possible. So if somebody is curious why Oumuamua was discovered now and not maybe 20 years ago, the answer is simple, because 20 years ago, our surveys were not that sensitive. The name is funny, as I said. It's from the language of native Hawaiians, and it means the first scout. So O means to reach out for something, Mua means the first, and another Mua emphasizes the former. So it's like the first scout, which is what it really is. I think the choice of the Hawaiian language was dictated by the location of the Pan-STARRS telescope, but also by the fact that the US is struggling with the construction of the TMT telescope on Mauna Kea. So I think it's partly this reason too. Now, in this animation, you can see that Oumuamua entered the solar system from above the ecliptic, then passed very close to the sun, around the same distance as the orbit of planet Mercury. And then later it passed very close to the Earth and started moving away from the planetary region. Let me play it again. So now we have the sun encounter and then the Earth encounter. And these are both close encounters for planetary astronomy standards. This was already kind of interesting, and with my colleagues, we started speculating wherever or not Oumuamua is a UFO. Because if you are entering a planetary system after a long journey, the first thing you want to do is to get some heat, get some energy, and then visit the most interesting planet in the system. And of course, our Earth is the only planet with biology in the solar system, as far as we know. So it wouldn't be a bad strategy for aliens, I would say. We will come back to the alien hypothesis later on. Now, it was very easy to realize that Oumuamua is coming from outside the solar system because it traveled on a very fast orbit. Here you can see an illustration showing a typical weakly bound Oort cloud comet originating from the solar system. It's shown in red. And the plot shows you the distance from the sun versus time. And as you can see, after perihelion passage, even a very weakly bound Oort cloud comet is moving away very slowly. However, Oumuamua traveled with a very high speed, and even at sort of infinity, its speed versus the sun was comparable to the orbital speed of the Earth. It was close to 30 kilometers per second. So it entered the solar system with a very high speed, and this resulted in a strongly hyperbolic orbit, which was very easy to identify almost instantly. I mean, within a week or so, it was completely clear that this object is not from the solar system. On the sky, Oumuamua arrived from a direction not far from star Vega, which is interesting because in the Contact movie and book, the signal from the aliens came from star Vega. So it was almost like the movie scenario materializing in our real life. Well, the truth is that, that of course, when Oumuamua was far away from the solar system, Vega was not where it is right now. So it's a pure coincidence. However, you can also see a point marked here with a purple dot, and this is solar apex. This is the direction on the sky in which our sun is traveling. And that's exactly from where you would expect interstellar objects to arrive, because, you know, it's like your front glass in your car. That's where most insects end up when you travel with a high speed, or that's where most rain accumulates when you're driving in the rainy weather. So in this sense, it was perfectly consistent with interstellar origin of Oumuamua. Now, when this object was discovered, it was already moving away from the sun and also very close to the Earth, and also starting moving away from the Earth. So not only was it faint, but also fading very quickly. At that time, the moon phase was increasing. So combining the moon phase and this rapid fading, it was clear that we had only perhaps 2 weeks for sensitive observations to be done. So that was really not much time. And we all had this feeling that we might lose this object before we even learn anything about this. So several teams started a race for observing time on some of the best telescopes on the Earth. And 3 teams were actually successful on 8 to 10 meter class telescopes. And our team from Cracow here was awarded the largest amount of observing time on this large telescope. So we obtained 12 hours on Gemini North. So that's Gemini North. And we split our time into observing nights. This is the first night. This is the moon. As you can see, the weather is fairly clear. And this is the second night, and the weather is also very good. Now, it was, of course, not very easy to win that much time on a large telescope, and to win this time almost instantly, we used the director's discretionary time opportunity. And but first, of course, when we learned about Oumuamua, we didn't know what to do. I remember that day very well. It was 25th of September when Piotr Guzik, a colleague of mine, called me and said, "Michal, you know what? There is a new minor object which has an eccentricity of more than 2. And of course, that meant that there is an arrival from the interstellar space. We kind of were prepared that this might happen one day. These interstellar minor bodies were speculated about for decades. But we didn't really believe that this might be now. But when we realized that this is really happening, we understood that this is a big moment for planetary science and for astronomy in general. So around 9 p.m., our team met in the very room in which I'm sitting right now at the Jagiellonian University. And we started, scratching our heads and thinking, what shall we do? We didn't know what to do because we didn't have any Oumuamua before. So we were kind of prepared and unprepared at the same time. And we had different ideas, honestly. We thought that maybe we should just collect every photon possible on any telescope that we can put our hands on, because this is such an original object, such an unexpected object. It can be anything, in fact. So maybe let's just collect photons. But then we realized that we cannot write that many proposals in a short time. So we decided to do what we can using standard tools and techniques of a solar system astronomy. So we treated Oumuamua as if it were a typical comet or an asteroid, which paid off, and it turned out to be a good strategy. So we met at 9 p.m. and around 3 a.m. in the morning, we submitted our proposal to Gemini. And half an hour later, the proposal was approved. It was fortunate that 3 a.m. in the morning here in Cracow was early afternoon in Hawaii, so the director of Gemini approved this proposal almost immediately. Unfortunately, the first night in Hawaii was not that good, but the following 2 nights, as you saw in these 2 movies, were very good, and we started collecting data. We took both imaging data. We wanted to see how the brightness of Oumuamua changes with time, and we also took spectra. Of course, all this time, we had one key question: what this object really is. Well, is it a comet? Well, perhaps, because interstellar comets were speculated about for decades. Well, but maybe it's an asteroid. Well, that's still possible. But maybe, maybe it's something else. We have never seen anything like that before. So we were prepared for everything, basically. And by the way, by saying we, I mean our small planetary team here in Cracow, which is Piotr Guzik, Basia Hanslik, Sebastian Kurowski, and Wacek Waniak, and myself at that time. And now we're also supported by Mikołaj Saba. So that's we. Okay, so this is what we found. I show you now our results, and if I'm presenting results which are not ours, this will be explicitly noted. So most of this stuff is ours. So the first thing that we saw in our combined image, and this is a very deep image, an over 3-hour effective integration on an 8-meter telescope, is this. Basically, a bright point of light, slightly blurred by the atmosphere. And this was kind of disappointing. All this effort and just a bright point. But at the same time, it's very interesting because this clearly shows that Oumuamua is not a comet. It has no coma, no tail. There is no characteristic signs of cometary activity in this image. And this is the most sensitive image of Oumuamua ever obtained by anyone. So it's definitely not a comet. By the way, these dark dots here are not miniature black holes. These are negative images of Oumuamua itself, produced by our background cleaning algorithm. So don't panic. These are artifacts. This is what is important in this image, this bright point of light. So this image is a stack of over 400 individual images that we took with Gemini over these 2 nights. Now, as I said, it's very interesting that Oumuamua is not a comet, but possibly an asteroid, because intuitively, we expect that interstellar minor objects will be predominantly comets. And the reason for that is very simple. Comets form at larger distances from their host stars, where the temperatures are low, and so that ice can survive. Ice need low temperatures, obviously, to survive. Whereas asteroids form much closer to the stars, where the temperatures are hotter, and therefore ice cannot easily survive on asteroids, and thus asteroids are rocky. And of course, objects which are farther from the stars are not as strongly bound by to these stars as the objects which are closer. And it's much easier to perturb an orbit of a more distant object so that it eventually end up leaving a planetary system. So comets are they are not as strongly bound to their host stars as asteroids. So we expected Oumuamua to be a comet, but it turned out to be an asteroid, which was the first big surprise. Now, we also scrutinized our individual images, and we realized that brightness of Oumuamua changes quasi-periodically. Here you can see the data phased according to the best periodicity solution. It's consistent with the rotation period of a little bit over 7.5 hours. But more interestingly, the range of brightness variation in the light curve is tremendous. Here in the upper panel, you can see the light curve in the units of flux. These are linear units. And in the bottom panel, in the units of magnitude, which is, of course, a logarithmic scale. So as you can see, the brightness changes by a factor of 11 or 2.6 magnitudes. And this is huge. In fact, such a large brightness variation has never been observed for any solar system asteroid. So that was another surprise. And to put it in context, here you can see histograms showing light curve properties for over 16,000 well-characterized solar system asteroids. And in this context, the red line shows the value which we measured for Oumuamua. Now, in the solar system, we have kind of two populations of asteroids, small asteroids, which are monolithic blocks held together by strong material strength. And they have slightly different properties than larger asteroids, which are mostly held together by self-gravity. So please have a look. If we look at the light curve range, these are these two upper panels. This is the light curve range. Oumuamua has this range of 2.6 magnitudes, which is indicated by this line. And this range is, as I said earlier, is greater than ever observed, either in the population of small asteroids or, in fact, in the entire population of asteroids, which is really remarkable. Now, when it comes to the rotation period that we measured, this value of 7.5 hours, the rotation period of Oumuamua is kind of slow or long compared to the typical rotation periods of small solar system asteroids, but it's typical if we compare Oumuamua against the entire population of solar system asteroids. And the reason for this is very interesting. It was suggested to me by Agnieszka Kleszczyńska. The possible scenario is as follows. The small solar system asteroids rotate mainly very fast because they had enough time to accelerate their rotation as a result of the Yorp effect, which is basically asymmetric heat radiation. This is a strong effect. Well, maybe it's not very strong, but if you wait for billions of years, it can accelerate the rotation period of an asteroid very significantly. And if Oumuamua is small, and there are reasons to believe that it's small, the fact that it's small and is rotating quite slowly might indicate that it left its planetary system before it accelerated its rotation as a result of the Yorp effect. If this is true, that would be consistent with the scenario of early ejection of minor bodies from planetary systems. So it might be that, in other words, it might be that the rotation of Oumuamua has not been processed by this asymmetric heat radiation. All right. We also did a very detailed light curve modeling. This work was done by Wacław Waniak. And without going into details, here is the flux ratio, and we wanted to convert the flux ratio into the physical axis ratio of this object. And this is, of course, impossible because we don't know how the axis of rotation is oriented. But we can place a robust lower limit, and this lower limit for Oumuamua is 5. I mean, the object axis ratio might be 5:1 to explain the factor of 11 brightness variation. And this is interesting because previous works made somewhat simplified modeling, and they inferred that the minimum axis ratio is equal to the flux ratio, and this is simply not true. The previous authors neglected realistic surface scattering properties and phase effects, which are important for an object such as Oumuamua. Now, let me check the time. Okay, we can, if we know the rotation period and have an estimate of the axis ratio, we can play a little bit with these two properties to estimate the minimum density of this object. Now, without going into details of this equation, and this is the only equation in this presentation, I promise, without going into details, I will just say that this equation shows what is the critical rotation frequency that a body can sustain. This is PC is the critical rotation period. This is the gravity constant. This is density. And this factor here in the bracket is a simple function of the axis ratio. Well, the axis ratio is given by F. And this part is responsible for material strength. But for larger minor bodies in the solar system, material strength can be neglected, so we can easily forget about this part for a moment. And then we have a very simple relation between the critical rotation frequency or period and density and axis ratio. Very simple, very simple. Now we can plug our measured rotation period and our limit to the axis ratio, and then we can obtain the critical density that is needed, the minimum density that is needed to help the material, the matter of this body together. And the result is over 1,000 kilograms per cubic meter. And this is the first value that we obtained for Oumuamua, which is absolutely typical, because typical densities of asteroids in the solar system are exactly in this range, around 1,000 or 2,000 kilograms per cubic meter. Now there is one funny story about this, because other teams found using exactly the same reasoning, much higher minimum density, reaching up to 25,000 kilograms per cubic meter. You know, 25,000 kilograms per cubic meter is greater than the density of gold. And of course, this is, well, it was concluded by these authors that this density is not physical. And so the density might actually be lower, but the body is held together by non-negligible tensile strength. So then this part came into play. However, these authors used a simplified version of this formula in which this term in the bracket is simplified by the axis ratio. It's a good simplification. However, unfortunately, they took the axis ratio in square instead of in the first power. So it's a stupid mistake which happened simultaneously in 3 papers, including a Nature paper by Karen Mitch, which is kind of funny because it shows that that all three teams were reviewing their own papers, and they shamelessly propagated the stupid mistake and concluded this unrealistic density or non-negligible tensile strength. Our result is that the body might have a typical density and still negligible tensile strength. Wherever tensile strength is negligible for Oumuamua or not, this is something that we don't know, but it can be negligible. That's what's new in this density discussion. Now, if you look carefully at this light curve, and this is, by the way, the best light curve of this object ever obtained, you can see that even though it's very good, the noise is low, the light curve doesn't repeat exactly from one night to another. Well, for instance, here, the blue points are clearly higher than the red points, and here the blue points are not really following the red trend. This is in the units of flux, but in magnitude, we can see exactly the same. So the reason for this was not very clear to us initially. At first, we thought that maybe we did something wrong with the data reduction, because the error bars are really small and it really shouldn't be like that. Then we thought that this could be due to some unknown instrumental effects, or maybe even clouds or birds or anything like that. But after a while, we realized that we really have no instrumental explanation for this discrepancy. And after long discussions, we concluded that there is nothing wrong with the data, that in reality, the light curve of Oumuamua doesn't repeat exactly from one rotation cycle to another. And this is a very interesting behavior, because it shows that the object is not rotating in a simple manner, like most objects like this, around a single rotation axis, but in fact, it tumbles in space, and therefore its rotational light curve doesn't repeat exactly from one rotation cycle to another. This behavior is not unheard of. It has been observed in the population of solar system asteroids and comets. And the usual explanation is that cometary tumblers behave like this because of outgassing. But of course, we didn't see any signs of outgassing in Oumuamua. So then there comes another explanation which applies to asteroids, and it says that tumbling is a result of collisions. So then all of a sudden we understood that Oumuamua comes to the solar system from far away, and it brings to us a very interesting message encoded in its rotation. And this message is that Oumuamua experienced a violent collision in its home planetary system. And it carried this message in the way it rotates during this very long interstellar journey. So that's very interesting, but it also agrees with the fact that dynamical instabilities not only eject minor bodies from planetary systems, but also these instabilities chaotize orbits of minor bodies, and chaotic orbits can easily cross, and collisions might be common. Now, this is a movie how tumbling looks like. And this is an illustration for the expected collision. All right, let's move on. The light curve of Oumuamua was very exciting, and this is in contrast to the spectrum. This is a Gemini spectrum of this object, and it's according to one of the editors of the Science journal, this is the most boring spectrum that he had ever seen, and it really is. There is no features, no emissions, no absorptions, no nothing. It's just a straight line with some slope. Well, this spectrum has been normalized to unity here. And as you can see, it has some slope. And this slope basically tells us that the color of Oumuamua is slightly reddish, and that's it. Now, other teams published less sensitive spectra, and based on the color, they concluded that Oumuamua has an organic surface. I mean, come on, there is no signs of organic surface. It's just reddish color. And I can think of hundreds of reddish colors which might not indicate organic surface. So the truth is that we don't know what the surface of Oumuamua is made of. We only know that it's slightly red. And I'll come to what we don't know in a second. Now, the final piece of information about Oumuamua arrived already several months after the observing campaign was over. And this is not our result. This result was published by Micheli et al. In Nature. And it's a discovery of non-gravitational acceleration in the motion of Oumuamua. This is a very exciting discovery. It basically tells us that the orbit of Oumuamua was not shaped entirely by the gravity of the sun and the planets, but there was also an unknown force acting on the motion of this object. What is this force? Nobody knows for sure. Now, non-gravitational forces have also been observed in the solar system. They are particularly strong for comets, but it's easy to understand because comets lose mass constantly when they are close to the sun. And as a result of this mass loss, they are pushed from their gravitational orbit. So this is a strong effect and known for many decades or even centuries now. Non-gravitational forces are also observed for asteroids, but only for very small ones. And these forces are extremely weak. They are again caused by asymmetric heat radiation. Now, the problem with Oumuamua is that it looks like an asteroid. There are no signs of mass loss. However, the strength of these non-gravitational forces is among the highest ever observed in the population of most active comets. So this is something which we still don't understand. And since this paper was published, there is a constant stream of papers proposing what might be the cause of this non-gravitational forces. And among these papers, there is a paper by Biele and Lepp suggesting simply that Oumuamua is an UFO, which might be true. Nobody knows. And anyway, let me quickly explain this figure because it might be a little bit enigmatic. I already told you what it means, but let me now tell you what it shows. So here is the left column shows the typical orbital solution using only gravity. And the right column here shows an improved orbital solution which takes into account this non-gravitational acceleration. And here are the astrometric residuals given in the units of standard deviation. This is a little bit counterintuitive. So these are in right ascension and these are in declination. So as you can see here, occasionally the deviations of the observed positions from the best gravitational fit reach 10 sigma. And there are many instances when the deviation is very large. And after inclusion of non-gravitational accelerations, the fit is basically perfect. So this shows that the detection of these non-gravitational forces is very robust. In fact, if you compare the gravitational solution with this solution that includes non-gravitational forces, then the deviation at some point reaches 22 arc seconds. So this is something that you could normally realize by looking at Oumuamua with a telescope and an eyepiece. This is a very significant effect. That's what I want to say. Now I think I'm slowly running out of time. Łukasz, can I go a little bit over the time limit, or should we finish sharply?
Well, there will be less time for questions.
Okay, so let me now then quickly summarize. First of all, what do we know about Oumuamua? All we know is that this object was very faint and that it showed very large, unusually large brightness variation. We have not seen any signs of ongoing outgassing, even in the most sensitive images. We also can say that Oumuamua had a reddish color, and very surprisingly, it experienced very strong non-gravitational acceleration. Now, what we don't know, we don't really know the size. Some people say the size is 80 by 400 meters, but this is under an assumed albedo of 4%. And this is a typical albedo for comets, but we have no idea what the real albedo of Oumuamua was like. Now, shape. I said that we found the limit on the axis ratio 5:1, but this is under a silent assumptions that the variability of brightness was caused by the fact that Oumuamua was periodically exposing greater and smaller cross-section like this. Now, I can easily think of a different mechanism generating brightness variation, and this is if Oumuamua was painted white on one side and painted black on the other side. In that case, the shape might even be perfectly spherical. So we're not really sure about the shape. Now, density, yes, we have this estimate of about 1,000 kilograms per cubic meter, but this is under multiple assumptions, including the rotation period and the shape. And of course, if the shape is different, then the light curve is not double peaked, but single peaked, and then the rotation period is different. Now, we don't know what chemical composition of Oumuamua is like. Really, we have no clues. And most significantly, we have no idea what was the nature of the observed non-gravitational forces. Now, because of these very large gaps in our data, many teams tried to fit in these gaps various scenarios. And I want to emphasize that this is simply exploration of the space of what is possible. Well, if you have very big gaps in your data, then essentially everything is possible. And now let me quickly list the most interesting hypotheses, which are not proven. There are no data can prove or disprove these suggestions. So some people suggested that Oumuamua was in fact a dust cloud. Some other suggested that it's a comet which underwent fluidization when its host star went through the phase of a red giant. Then some other people said that it's a comet which lost volatiles. Biele and Leb suggested that it's a UFO, or strictly speaking, a cosmic sail that was sent to us by an alien civilization. Some people suggested that it might be a piece of dark matter. Then some other people suggested that it's in fact a normal comet with unusual dust, with basically invisible dust. Nobody knows what invisible dust is. And then two more very recent suggestions are that Oumuamua was made of hydrogen ice or nitrogen ice. Well, as I said, none of these hypotheses can be proven or disproven based on the data obtained. So let me stop here, and thank you for your attention, and I'd be glad to answer your questions.
Thank you very much, Michal. I think we can do it for real. You could hear us. Let's try with a couple of questions. Maybe we can start here with the audience. Are there any questions here? You can raise your real hand. Okay.
Hello, Michal Szymański. The question is, I might have missed you saying that, so either you please repeat or tell us. How do you know the two episodes of the resonance between Jupiter and Saturn in an early history of the solar system?
Okay, it's a good question. So these are results of theoretical modeling. And let me scroll back to the original slides so you can have a look at the references there. Okay, so the first episode, chronologically the first one, was inferred in a paper by Walsh et al. And it is called the Grant-Tuck hypothesis. And it's basically a result of a numerical simulation. It explains several observed properties of the solar system. So in this sense, it makes sense. However, this type of simulations usually cannot predict anything. So they only provide an explanation of what is observed. And the second one is called the NIS model, and it was published in 3 papers in Nature in 2005. And this is again a result of numerical simulation, which gives an output that is consistent with what we observe. It is consistent with statistical properties of the present-day Kuiper belt and of the orbits of the outer planets. But again, the main problem with these simulations is that they have so many free parameters that you can always explain everything that is observed. So yes, that's my answer.
Okay, thank you. The next question is from Zoom, Krzysiek.
Hi, Michal, very nice talk.
Hi, thanks.
So I have a question about the figure you shown on the non-gravitational acceleration.
Oh,
yes, this one. So you say that this is unknown non-gravitational acceleration, right? But to go from left panels to right panels, you need to somehow model this acceleration, right? So what is assumed here?
Okay, so it was simply assumed that the force is proportional to the heliocentric distance in some power, and the best fit shows that this is power of -1 to -2. So -2 is interesting because that's how the amount of radiation declines as you're moving away from the sun. So that's why people like this explanation of solar sail. And in that case, the nature of this force would be radiation pressure. But also the amount of outgassing declines roughly with the inverse square of the heliocentric distance. So this is also a possibility. But mathematically speaking, this force is proportional to the heliocentric distance to -1 or -2. They couldn't really tell which exponent. Well, the difference is not significant between these two exponents.
So there is a there is a mathematical model very well describing the data, but no one can say what it is physically, right?
Precisely. We know the mathematics of this force, but we don't know what it physically is. We can only tell that the force was declining with the increasing distance from the sun, and this makes sense because this force might be related to the sun in form of, as I said, heating or radiation pressure. But we're not sure, and it could be a UFO still.
Okay, thank you.
Okay, thank you. Are there any more questions here?
Hi. So my question is rather broad, and it's: would Oumuamua, being a comet with some unusual dust, would it explain all these mysteries, or is it not enough, or you can't tell?
Well, if it is a comet, then everything is possible due to mass loss. And so yes, that's the original explanation by Micheli et al. In their Nature paper, they listed several possibilities. And from these possibilities, they concluded that it's probably a comet experiencing some sort of invisible outgassing. So yes, the cometary hypothesis explains this non-gravitational acceleration, but then we need to have invisible dust. So you're moving something peculiar from one area to another area. There is no plausible explanation that explains Oumuamua entirely, and that's a problem.
Okay, thank you, Michal. I don't see questions here. I don't see anything on Zoom. I have one, if I may, about the origin. You said that there were some people saying it came from Vega, but given all the uncertainties and the collisions this body experienced, how precisely we can estimate the actual origin of that? Okay. Which solar system it came from?
It's a very good question, and there were people trying very hard to find the star. And in fact, this was a rationale for the Hubble Space Telescope observations of Oumuamua when it was already very faint and too faint to observe with the ground-based telescopes. We needed a large arc so that the orbit could be established accurately, and there were hopes that a star could be found. But these efforts completely failed, not only because nobody could find a star matching the trajectory of Oumuamua, but also because of this non-gravitational acceleration, which is not that well established. I mean, I'm talking about accuracy right now. I mean, it's certainly there, but it kind of makes difficult to extrapolate the orbit to another planetary system. Now, but collisions are not a problem because we believe that Oumuamua experienced a collision at its home planetary system. So this wouldn't affect the direction from which it originated. And we're sure that it didn't experience a collision in our solar system because the probability of such a collision is extremely low. As you saw, Oumuamua came from the direction above the ecliptic where the density is low. So the chances that it collided in our solar system are extremely slim, and also the interstellar space is not that dense, so we're pretty sure that it didn't collide there either. But we don't know what is Oumuamua's home, and that's unfortunate.
Okay, thank you very much. I don't see any questions, so let's thank our speaker. Thank you, and I'll stop the recording and the transmission. Thank you, and see you next week.
Thank you very much.